Salutations! This is a presentation for EVE310 assignment number 1, the ELEGOO challenge. My name is Alan Ho.
And my name is Cameron Handy. Starting with methods, the challenge was to design, build, and program an automated monitoring system using the ELEGOO kit, which has the purpose of understanding a societal challenge. Our particular objective was to build a portable desk fan that turns on and off depending on the temperature conditions of the room. Team members needed to design the circuit, find the optimal temperature for the fan to operate, and write the code.
Now for our methods flowchart. We first have to obtain the ELEGOO starter kit, which we received from the CAEE department. Then we gather the libraries for the sensors that we utilize in our device. After that, we designed the circuit in Tinkercad and wrote the code for our device in Arduino IDE. Then we built the device after our model in Tinkercad using supplies we got from our starter kit. When we finished making the device, we had to upload the code into the ELEGOO and troubleshoot any errors. After we fixed any errors that might have appeared, we deployed our device in our workspace so we can enjoy cool air.
We created our prototype in Tinkercad. The DHT11 temperature and humidity sensor was connected to digital pin 13 and extracted data every 4 seconds. This sensor was connected at digital pin 13 because the signal would convert automatically from analog to digital. Lastly, the motor was connected to pin 2 and turned on and off when a certain temperature was reached.
The code for the device is very simple. We first had to include the library for the temperature sensor, and then picked our pins for our sensor and motor by establishing variables. As modeled in Tinkercad, the sensor is on pin 13 while the motor is on 2. Then we set up a serial port so we could read our temperature and humidity values and set up our motor pin as an output. Afterwards, we used the code given in the template to take measurements of temperature and humidity every 4 seconds and had to display our measurements in the serial monitor. Finally, we have 2 if conditions to tell the motor to turn on or off at a certain threshold of 25 degrees Celsius.
Now, you may be wondering, why turn on the fan at 25 degrees Celsius? Well, actually, the temperature at which the fan operates can be adjusted to suit personal preference, but we discovered through a study from Cornell that the optimal temperature for productivity is at 25 degrees Celsius. Beyond that temperature, the fan would turn on to cool the user, creating a more suitable environment.
Now for the application. We decided to monitor and deploy the fan at a student's desk for 1 hour. By doing this, we could see if the fan had any effect on cooling down a room for a student doing homework. It turns out the fan turning on has no correlation with the temperature of the room at all. We can see from the data that even though the fan was on for around 15 minutes, the temperature still increased from 27 degrees Celsius to 28 degrees. This is because a fan does not actually make a room cooler. However, the fan creates a wind chill effect. By blowing air around, it makes it easier for air to evaporate sweat from the skin, eliminating body heat. It also helps circulate air to prevent temperature gradients in the room. The temperature in the room mainly depended on outside factors, such as if the AC was on, if a desktop was on, or if a lamp was on, which all can contribute to the temperature of a room.
On to the discussion. Our team had to meet to brainstorm ideas for the project, design our circuit in Tinkercad, write and test code in Arduino IDE, and finally build and troubleshoot the device. The process went along smoothly, with the largest roadblock coming from a faulty motor provided in the ELEGOO starter kit. A wire had completely disconnected from the motor, so it had to be soldered back on in order to continue our challenge. The circuit design was a little confusing at first, as we were unsure which prong on the temperature and humidity sensor corresponded to the voltage signal. But after reviewing the manual in the library download, it cleared things up. Coding was painless and was extremely similar to the template code that was provided. All we had to do was add if conditions for the motor. Lastly, team coordination went along famously. Work was divided up and conquered, and there was a lot of communication between partners.
Now for the assessment of our finished design. Some pros of the device was it was portable. You can use it wherever you take your laptop and it's just plug and go. It can also be wireless if you're using a battery. The fan turns on and off automatically and is relatively inexpensive.
Looking at the cons of our device, we found the fan to be quite weak, so we hardly felt any air. The fan did not come with a mount, so it was difficult to position the fan effectively. Lastly, at the temperature boundary of 25 degrees Celsius, the fan would turn on and off rapidly.
To address the cons and ensure a better prototype, a higher voltage battery could be used in order to provide more power to the motor, and as well a more powerful motor which can handle the higher voltage. We can also create a mount for the fan so it can be easily mounted onto the desk using Maker Studio's 3D printers. And finally, we can take measurements of the temperature at less frequent times so the fan would blow for at least some time period before turning itself off.
Regarding the challenges of our project, as I said previously, the flimsy nature of the wires on the motor was an issue that was anticipated due to the inexpensiveness of the kit. We resolved this issue by asking a friend to solder our equipment. Another challenge arose during data collection because the putty session was not logged correctly, and an hour of data was not saved. We reviewed the data saving file and successfully collected data. Overall, we were satisfied with how we responded to these challenges.
We wanted to discuss further applications of this simple fundamental process in our device. We can apply it to things such as fan for electronics. For example, when at a high CPU temperature, a fan would automatically turn on to cool the hardware and prevent device shutdown. Another example of this process used in everyday life is air conditioning. When a thermostat senses a temperature that is too high or low, the air conditioning in the house would turn on to cool or heat you up. Thanks for watching! Please comment, like, and subscribe!